The content in this presentation is covered on pages 154 through 166 of your textbook, and it's meant to help you achieve learning objective number 26, which is to explain the roles of adiabatic cooling and cloud condensation nuclei in cloud formation. Be sure to at least skim pages 154 through 166 before you watch the video, and to read the chapter carefully before you attempt the online quizzes. Clouds consist of billions of minute water droplets and ice crystals that are suspended above Earth's surface. In addition to being prominent and sometimes spectacular features in the sky, clouds are of continual interest to meteorologists because they provide a visual indication of atmospheric conditions. It's one of the things you can do, in other words, to learn how to read the sky. For condensation to generate clouds, the air has to reach a saturation point, and there has to also be a surface on which the water vapor can condense to form the liquid droplets. Remember how we change the relative humidity in an air parcel? We talked about a visual or a thought experiment in class the other week. We can either change the temperature of the container or the air parcel, or you can add or subtract moisture. Two different ways of making saturation happen are exactly the same. You can either lower the temperature of the air parcel to its dew point temperature, or you can add water vapor by pushing a thirsty air parcel over a nice warm body of water. The most common way that clouds are made is when an air parcel rises and cools adiabatically to its dew point temperature. So that's its 100% humidity condition. Remember that when an air parcel ascends, it passes through regions of successively lower air pressure, right? And that causes the parcel to expand and cool adiabatically, right? Without adding or subtracting heat from the parcel. At the point where the parcel can no longer hold any more water vapor, that vapor condenses to liquid molecules and latent heat is released. So if you could measure the relative humidity using a sling psychrometer right at that point where a cloud is forming, you would see that the dry bulb or the ambient air temperature and the wet bulb, the dew point temperature, are exactly the same. And so that tells you you have a condition where the relative humidity is at 100%. You can see in the diagram on the left here that the air in the cube is rising due probably to convection. The ground surface temperature is probably at or about 87 degrees Fahrenheit because the air above the ground is at 87 degrees Fahrenheit. But you can also see that it's cooling at a rate of about 5.5 degrees Fahrenheit per 1,000 feet. That's the standard rate that we've been using, but we've been talking about kilometers instead of feet and degrees C. So another way of saying the standard dry adiabatic rate is 5.5 degrees Fahrenheit per 1,000 feet. But remember from the mountain problem worksheet that the dew point temperature doesn't decrease until the air is saturated. And one of the things that people got wrong on the last test was that that dew point temperature decreases not at 2 degrees once the air is saturated. Remember, that rate is for the dry adiabatic rate of dew point temperature changing. It follows the same rule as the moist adiabatic lapse rate. So when you get to, with a dew point temperature of 65 degrees, and a dry adiabatic lapse rate of 5.5 degrees Fahrenheit per 1,000 feet, we could expect saturation, or 100% relative humidity, to occur at 4,000 feet, and that would be the liquid condensation level. So in your head, look at this diagram here, maybe try drawing it once or twice, and a good way to practice for a question that might show up on the final exam would be to just make sure you understand the math that's going on in this slide. So we start off with a dew point of 65 and a surface temperature of 87. And by the time we've gone up 2,000 feet, if the rate is 5.5 per 1,000 feet, we know we should be about 11 degrees cooler. And remember that the dew point does not change until saturation occurs. So if you were given a dew point temperature or a wet bulb temperature, and you were given the air temperature or the dry bulb temperature, and you also know the dry adiabatic lapse rate, you can predict the elevation where the clouds start to form. That's the cloud base, or the liquid condensation level. So I think you can do that. You have all the knowledge you need, and you even understand some of the physical processes behind it. But another way you can form a cloud is to move, like you see in this picture up here, a relatively cool and dry air parcel over a relatively warm body of water. So you can see that this body of water is not frozen. The air above it is below freezing. So we just need to see relatively warm water, and I would not go swimming in that water. But the air mass moving over it is lower in temperature and relatively dry. So when that occurs, you can add water vapor to the dry air parcel through evaporation. And this is the main process responsible for formation of low clouds. So especially those that you find in subtropical oceans. That's convection to some extent, but a lot of it is just the fact that we have cool, dry, relatively cool, dry air passing over warm water. Another requirement for condensation is that there has to be a surface in most cases for the water vapor to condense. Objects at or near the ground, like blades of grass, are that kind of surface that I'm talking about. So when condensation occurs above the ground, aloft, tiny particles known as cloud condensation nuclei serve that same purpose. So without the condensation nuclei, a relative humidity well in excess of 100% is needed to produce cloud droplets. And that can happen. At very low temperatures, a low kinetic energy, water molecules will actually stick together in tiny clusters, even in the absence of any condensation nuclei or any surface to form on. But that's not most cases. We find things for water to stick to in the sky from a number of different places. Dust storms, volcanic eruptions, pollen from plants. All of those are major sources of cloud condensation nuclei. In addition, condensation nuclei are introduced into the atmosphere as byproduct of combustion. So whenever something burns. So that could be a forest fire, could be your automobile, could be coal-burning furnaces. The most effective particles for condensation aloft are hygroscopic, not hydro, but hygroscopic. And that means water-seeking nuclei. So common food items like crackers and cereals are hygroscopic. When exposed to humid air, they absorb moisture and quickly become stale. But we don't see, I think that the number of condensation nuclei in the atmosphere that come from saltine crackers is probably pretty low. But over the ocean, salt particles are released into the atmosphere whenever sea spray evaporates. They're tiny little particles. Because salt is hygroscopic, water-seeking, the water droplets begin to form around the sea salt particles at relative humidities that are much less than 100%. As a result, cloud droplets that form on hygroscopic particles, such as sea salt, are generally much larger than those that grow on hydrophobic or water-repelling nuclei. Although hydrophobic particles, water-repelling particles, are not very good condensation nuclei, cloud droplets will form on them when the relative humidity reaches 100%. Because cloud condensation nuclei have a wide range of affinities for water, cloud droplets of various sizes often coexist in the same cloud. That's an important factor for the ultimate formation of precipitation. Initially, the growth of cloud droplets occurs really quickly, but the rate of growth slows down as the amount of water available for consumption by a huge number of competing droplets begins to decrease. So the result is the formation of a cloud consisting of billions of tiny water droplets, usually having diameters of less than 20 micrometers. These clouds droplets are so minute that they remain suspended in air by even the smallest little updraft. Even in very moist air, the growth of cloud droplets by additional condensation is very slow. The vast size difference between cloud droplets and raindrops, here's a raindrop in the bottom of this figure. It takes about 1 million cloud droplets to form a single raindrop. And that big difference in size indicates that condensation is not responsible for the formation of raindrops or ice crystals large enough to fall to the ground without evaporating. We'll look into that in chapter 7 when we talk about precipitation. Use the content provided on the Canvas site as well as outside internet sources if you'd like to go looking at NOAA or NASA to verify that you can formulate answers to these questions. If you can comfortably answer them, you're in great shape for the next midterm. If you can't, review the textbook, rewatch the video, see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.